Industry voice: climate change needs a moonshot. We're still building faster airplanes. Delegates at this week's Bonn Climate Conference are bringing knives to a gunfight. Our interventions for cutting greenhouse gas GHG emissions are puny relative to the size of the problem. To fight climate change credibly, we need to ramp them up by 2 orders of magnitude. Bonn is part of the UNFCCC process that produced the Paris Agreement to keep global warming within 1.5 to 2 degrees Celsius. To implement it, we need to cut emissions by at least 26 gigatons of carbon dioxide, or equivalent CO2e each year, and remove another 7 to 9 gigatons already in the atmosphere by mid-century. Human activity emits 56.4 gigatons, 56 to 400 megatons CO2e a year and counting. All carbon capture, direct air capture, sequestration, and offset programs add up to less than 1% of that. Similarly, the new state of carbon dioxide removal, found carbon removal today, is less than 1% of what we'll need to avoid catastrophic warming. The mismatch in scale drives impacts. Anthropogenic emissions have increased nearly 1.5% a year since 1990. Naturally occurring emissions are rising faster than any time in the last 50,000 years. Atmospheric carbon dioxide levels just hit another depressing high, 431 parts per million. The problem isn't a lack of know-how, it's a failure of imagination. Gigaton-scale carbon solutions are possible, we just haven't seriously pursued them. We've pursued what's comfortable and profitable in the near term, ignoring basic climate math. As a result, climate policy, investment, and voluntary regimes and pledges tinker at the margins while the problem accelerates 1,000 times faster than solutions. We've overcome such problems of scale before. Computer memory scaled by 9 orders of magnitude in just a few decades. In the 1950s, it was measured in kilobytes. By the 1980s, personal hard drives held tens of megabytes, then gigabytes a decade later. Today, we routinely store terabytes, billions of kilobytes in the cloud. Why? Because we envisioned the future and figured out how to build it, rather than incrementally improving on existing technology. Infrastructure, investment, and engineering follow imagination and ambition, not the other way around. Similarly, the Manhattan Project didn't incrementally improve artillery shells. It posited yield-to-weight ratios 1,000 times higher than anything seen before and engineered new ways to achieve it. When Kennedy announced the Moonshot, most engineers privately considered it impossible. NASA didn't get to the moon by trying to build faster airplanes, but by inventing entirely new systems, materials, and methods the goal demanded. Carbon management must learn this lesson and set its sights higher. Instead of incrementally improving kiloton-scale interventions, we should envision gigaton-scale solutions to restore the climate to pre-industrial conditions so humans and all life on Earth flourish. The financing and engineering will follow. Today, we're still tinkering incrementally. Direct air capture, DAC, removes less than 0.01 megatons of carbon currently and won't ever scale to gigaton levels. We'd need to build 10,000 large DAC plants at a cost of over $10 trillion to remove 10 gigatons of CO2 annually. There is no credible financing for that, and no proof that the huge amounts of energy these plants would require wouldn't emit more GHG than they remove. Yet we gave DAC the lion's share of carbon removal funding from 2021 to 2025 anyway, including $2.3 billion in private investment. Meanwhile, the voluntary global carbon credit market is surging, currently valued at $414 billion and projected to reach $1.6 trillion by 2028. It's a powerful financing mechanism, but it only rewards certain kinds of limited interventions that can be audited and traded. A megaton of CO2 injected into a saline aquifer generates carbon credits, while a gigaton-scale shift in ocean carbon sequestration does not. As a result, carbon markets enforce a structural bias towards smaller interventions that fit neatly into existing accounting frameworks and away from the large-scale ones that might actually work and restore the climate. Such large-scale solutions are possible, and we should invest in them. For example, concrete, the most used building material, has a giant carbon footprint. But it could be changed from a huge carbon source to a huge carbon sink. Limestone, or calcium carbonate, is a key ingredient in concrete. It's 44% CO2 and made almost entirely of fossils. Limestone formations like the White Cliffs of Dover and Pacific coral reefs permanently store many gigatons of carbon. If we changed the recipe, concrete could too. Concrete is a mix of cement, sand, and gravel. Its production uses 40 gigatons of limestone annually, the largest mass commodity on Earth after water. Some of that goes into cement production, emitting 2.8 gigatons of CO2 annually, 7 to 8% of global GHG. Cement substitutes might cut those emissions in half, 1.4 gigatons. But concrete could store 10 times that amount if we replaced quarried limestone aggregate, about 80% of concrete's mass, with synthetic limestone. In all, decarbonized building materials could safely, permanently store about 16 gigatons of carbon in the built environment each year. There are other promising gigaton-scale climate interventions, for example, ocean iron fertilization, but we'll never develop them by sticking with incremental tinkering and near-term market incentives. The Moonshot and the Manhattan Project began with honest reckoning of the scale of the challenge, then strained forward toward an audacious goal. So far, our climate interventions mostly duck the challenge and lean backward toward what is financeable. Restoring the climate requires gigaton-scale interventions. Only when our ambitions match that reality will we be in the right fight. Brent Constantz is the founder and CEO of Blue Planet Systems and a consulting professor at Stanford University.